Analytic techniques in clinical chemistry. The first technique we're going to start off with is spectrophotometry. This is the measure of the intensity of light at selected wavelengths. It isolates wavelengths using prisms or gratings, and the energy of light is inversely proportional to the wavelength. When we talk about wavelengths, we need to look at the different parts of what the human eye can and can't respond to. When you look at this picture, you can see a wavelength here on the top. We've divided it out between cosmic rays, gamma rays, X-rays, ultraviolet, infrared, and microwaves. The only area that the human eye is able to see is between 380 and 750 nanometers. This is where we divide up our colors of violet, blue, green, yellow, orange, and red. The lower part of the visible spectrum is ultraviolet, and the upper part would be infrared. In spectrophotometry, if the white light is diffracted or partially absorbed by a filter or prism, it becomes visible as certain colors. The color of light seen in the visible spectrum depends on the wavelength that is not absorbed, but that is transmitted. When the white light is passed through a solution, part of the light is absorbed, and the remaining part of the light is transmitted. Solutions contain particles that absorb certain wavelengths and transmit others. For example, a blue solution appears blue because particles in the solution absorb all of the wavelengths except blue. Blue is the color that would be seen or transmitted. When we use spectrophotometry, we use something called Beer's law. This is the relationship between the absorption of light by a solution and the concentration of that solution. It states that the concentration is directly proportional to the amount of light absorbed, and the intensity of the color is proportional to the concentration of the substance. I'm going to give you an example. I have a picture of a cup of beer on the top right-hand side. If you were to shine a flashlight through two different beers, one of them being a really strong microbrew, and the other one being a really weak domestic light beer, and you shine the flashlight through, the one with the least amount of absorbance, or that transmits the most of light through the beer, would be the light beer because it's got a lesser concentration of alcohol. Now when you look at the strong craft brew beer, it has a higher alcohol content, and you were to shine a flashlight through that, it would have a higher absorbance because it would absorb more of the light because of the dark color. More light would transmit through. So a certain amount of light is absorbed and a certain amount of light is transmitted. Because we're able to detect the amount of light being transmitted through the sample, or the beer in the example I gave you, we need to use an equation to turn the amount of light that is transmitted into the amount of light absorbed. So the only way we can do that is to use a logarithm function. So we'll take a photodetector, which I'll show you in a minute, that will pick up the amount of light that traveled through our sample, or our beer in this case, and use this equation to turn it into how much light was actually absorbed by the sample. The percent transmittance is the ratio of energy transmitted divided by the energy passing through the blank. The blank is just plain water. All light absorbed is 0% transmittance. 100% transmittance is all light is sent through, or essentially no light being absorbed. So if you were to put a flashlight through water, 100% of the light would go through. So that's 100% transmittance, 0% absorbance. If you used a black specimen, it would be 100% absorbed, 0% transmitted. Here's how we take that percent transmittance that we get from the spectrophotometer and arrive at the absorbance. The absorbance is what we're going to need to do all of our chemistry calculations. So absorbance is the amount of light absorbed by the sample. We can't directly measure how much light was absorbed, but we can tell how much light went through because we have a photodetector to tell us. This equation, absorbance equals 2 minus the log percent transmittance, can be done with a traditional scientific calculator. There's also some other things that are involved with this. When we talk about absorbance, you'll see it equals A times B times C, where E is the molar absorptivity, B is the length of light path through the solution, and C is the concentration of the absorbing molecules. We won't be referring to this or using this very often, but this up here, the A equals 2 minus the log percent T, is something you will need to memorize. All right, so the spectrophotometer I speak of, how does this work and what are the parts involved? I have all of the parts listed here of the spectrophotometer that you are going to be using in the clinical chemistry laboratory. And this measures the light transmitted by a solution to determine the concentration of the light absorbing substance. Let me give you an example. One of the first spectrophotometry labs you'll be doing is an albumin test on human serum. We are going to mix some human serum with a reagent, which again is the chemical that drives the reaction, and it's going to create a color in the test tube. The darker the color, the more albumin there is. The lighter the color, the less albumin there is. So we're going to be able to tell by the amount of light transmitted through the sample, through the test tube, how much albumin is there. Okay, I'm going to give examples in a little while of how we do that calculation, but first let's look at how the spectrophotometer does that. First, there's a light source. We need to transmit light through somehow, and usually it is a tungsten light bulb. Incandescent lamps are also used for visible or near infrared work, but if you want to get really technical and work in research labs, you'll find lasers, light amplified by stimulated emission of radiation, is what that stands for. Very focused beam of monochromatic light with the lasers. There's also deuterium discharge lamps or mercury arc lamps, which are used for UV work. For the majority of what we're going to do in clinical chemistry, we're going to use our tungsten light bulb. The very first thing we have to do before we use the spectrophotometer is zero it with DI water. We're going to take water, put it in the spectrophotometer, and we're going to tell it that this is 100% transmittance, 0% absorbance. So we're going to set that up. It's kind of like a little calibration telling it, okay, now this is what it looks like to have 100% of light shining through you. All right, the first part of the spectrophotometer is the monochromator. It's a system to isolate light of a desired wavelength and exclude other wavelengths. The filter is a simple type of thin layer of colored glass, and then we've got a series of prisms which separate light into a continuous spectrum through refraction, with shorter wavelengths refracting more than long wavelengths. This is rotated so that only the desired wavelength passed through the exit slit. So we have the light coming through over here. There's an entrance slit, and then we can pick the wavelength that you want. The manufacturer of the test will tell you what wavelength to use. There'll be a dial. So you can pick 340, you can pick 550. You can turn it to whatever you need, and that will turn that monochromator to isolate one wavelength. Then we have the diffraction grating. This is most commonly used. You can see it in the middle down here. It's based on the principle that wavelengths bend as they pass through a sharp corner. The degree of bending depends on the wavelength. It consists of many parallel grooves on a smooth surface, which split the light into several beams traveling in different directions. The directions of these beams depend on the spacing of the grating and the wavelength of light, so that the grating acts as a dispersive element. Just helps to get the light through. The next part is a cuvette. This is where your sample is going to be. Sometimes they're called absorption cells. They can be round, they can be square, they can be rectangular, they can be made out of glass, silica, or plastic. You have to have quartz for UV work though. They have to be clean and optically clear. As you can see, light is shining through your sample, and if you have fingerprints, bubbles, things like that, scratches on your cuvettes, don't use them, because that will scatter light in other directions that you don't want, rather than at your photomultiplier tube. So we want a nice clean ray of light shining through your cuvette. The next part is that photodetector or photomultiplier tube. It converts the light into an electrical signal that is proportional to the number of photons striking its surface. Examples of this would be a photomultiplier tube, a photocell, phototube, photodiode. I'm not going to go into details on those, but those are just examples of things that are able to detect photons of light. The next part is a readout device. The electrical energy from a detector is displayed on a type of meter or readout system, which could be analog or digital. On the campus that I teach at, there are both. I've got 2 analog and 2 digital. Students always seem to fight over the digital one. The analog just has a bar that moves back and forth to tell you what the absorbance might be. Then we have the recorders or microprocessors. On the typical spectrophotometers that we're using when this lecture was created, we just have to write down the results that we're getting. But in more advanced spectrophotometers or in the chemistry analyzers you'll see in the hospitals, they have spectrophotometers in them that relay the results onto a laboratory report. With the spectrophotometer, we do have to do quality assurance as well. We need to check the wavelength accuracy, any stray light, and the linearity, which again is how low can you go to how high can you go. So how do we get an answer for our test from those spectrophotometers? Well, we're going to write down the answers that we get when we put our samples in. You're going to take the absorbance reading of your unknown, which would be your patient sample or your human sample. The absorbance of a standard of known concentration. I have a picture of a vial down here, and we'll pretend that's a standard. You can buy that, and it will tell you this is exactly 100 milligrams per deciliter. So not only are you going to put your patient sample with reagent and test that, but you're also going to put the standard with reagent and test that too. Put that in and write down the results. You're going to take your absorbance results of your unknown or patient, divided by the absorbance that you got for that standard, and multiply it times the concentration of that standard. So you're essentially comparing all of your patient samples to that standard to get an answer. So in this case, if the absorbance of the unknown is 0.200 and the absorbance of the standard is 0.250, the concentration of the standard being 100, your answer would be 80 milligrams per deciliter. You will need to be familiar with how to perform this every week for your lab report, along with on your quizzes and exams. We do have different types of spectrophotometers. First one is an atomic absorption spectrophotometer. This is a technique for determining the concentration of a particular metal element in a sample. It's used in clinical labs to measure elements such as aluminum, calcium, copper, lead, lithium, magnesium, and zinc. There's also an emission technique in which an element in the sample is excited with a flame, and the radiant energy given off is measured as the element returns to its lower energy level, or ground state. Unexcited atoms absorb light of a characteristic wavelength. So what you see here in this picture is a light source. We then have a chopper which turns that light into little pulses of light, and we have the sample which, depending on it, I guess sometimes it uses like a burner or gas. Other times it could be an electrical type of thing that would atomize your sample. Okay, so your sample's down here. It aspirates, it's heated, and there's a burner head. So the light is shining at the atoms. There's a monochromator after that was picked up with a photomultiplier tube to give you a readout. What you're going to be familiar with memorizing for this is the fact that it tests for all these metals, and then the emission technique, as you see here, which you're going to have to memorize that definition as well. Fluorometry is our next one. This one occurs when a molecule absorbs light at one wavelength and re-emits light at a longer wavelength. The detector is placed at right angles to the sample cell, and a secondary filter that passes the longer wavelengths of fluorescent light prevent an incident light from striking the photodetector. The electrical output of the photodetector is proportional to the intensity of the fluorescent energy. So as you can see here, we got a light source. We got a filter that's going to come through, and it shines into the sample. Here's the right angle with a secondary filter and a photomultiplier. Then there's a readout. Again, you're going to need to memorize the definition of fluorometry. One of the things that we use fluorometry for is flow cytometry. A type of fluorometer used in hematology is the flow cytometer. It's the measurement of the physical or chemical characteristics of cells. So measurements are made while cells pass through in a single file line using a fluid stream. So they go through a single file. And the flow sorting uses electrical and mechanical means to collect cells with one or more measured characteristics. The laser-induced fluorometry that it uses and the particle light scattering analysis allow different populations of cells to be differentiated by size and shape. Now, you're going to go through more of this in your hematology courses, but some of the things that you can do is measure the forward light scatter, and it'll tell you the size of the cell. Is it small platelet? Is it a medium red cell, or is it a large white cell? The granularity is a 90-degree scatter. So that would be things like your neutrophils would have more granularity than, say, a lymphocyte. It can also look at DNA and RNA content too. The next type of analytic technique that we use is chemiluminescence. This is the emission of light when an electron returns from an excited or higher energy level to a lower energy level. Excitation event is caused by a chemical reaction. These are used a lot for things like hormones and things that are very small quantitation in the human body. We're able to actually take an antibody with a label on it and attach it to the antigen in question, and it will create a light. Chemi stands for the chemical reaction, lumi stands for the light. So it's a chemical reaction that creates a light that can be detected. This is used in automated immunoassay and DNA probe analysis systems. We also have enzyme immunoassays, which kind of fall in this category as well. The next one is turbidity or nephlometry, just as it sounds. Think of something with a high turbidity being something like milky, and something with a low turbidity being something clear like water. These are techniques used to scatter light. Light scattering occurs when energy passing through a solution encounters a molecule in a collision, which results in the light being scattered all over. Picture milk and all the little fat molecules inside of milk. If you were to shine a light through that, it would scatter light all over the place. Okay, there's lots of little fat particles in there. The measurement technique is used in the quantitation of serum proteins. A lot of times use it for things like immunoglobulins. Turbidimetric measurements are made with a spectrophotometer. Nephlometry measures light scatter at an angle to the beam incident on the cuvette. So some other things that you need to memorize. Here's an example of what it might look like. Nephlometry measures light scatter at an angle to the beam incident on the cuvette. The amount of scatter is determined by collecting the light at an angle. So in this picture, we have the light source, here's the cuvette, and a spectrophotometer or turbidimetry would measure light straight on. A nephlometer is going to take a measurement of the light coming out at 70 degrees or 90 degrees. Okay, so spectrophotometer goes straight through. The nephlometer is looking for light that's not just shined straight through, but that is scattered in other directions. All right, electrochemistry basics. Moving on to something quite different from spectrophotometry is we're using electrodes to try and determine the concentration of something in a sample. Make sure you know the difference between an electron and an electrode. An electron is a particle carrying a unit charge of negative electricity. Ordinary electric current is the flow of electrons through a wire conductor. The electrode is an electric conductor, usually made out of a metal, used as one of two terminals to conduct an electric current. We talk about something called potential, the electrical potential. This is the potential voltage that could exist between an anode and a cathode if they become coupled. The measurement of an electrical potential difference between two electrodes in an electrochemical cell is what we refer to. So we look at the potential difference as a voltage difference that can be measured, and we then turn that into a laboratory result. Here's an example of how electrochemistry works. A battery consists of two electrodes, usually one zinc and one copper, immersed in an electrolytic solution. When a chemical reaction occurs in the solution, electrons gather on the zinc electrode or cathode, which become negatively charged. At the same time, electrons are drawn from the copper electrode, the anode, giving it a positive charge. That difference in charge sets up a potential difference or voltage between those two. When they're connected by a conducting wire, electrons flow from the cathode to the anode, producing a current. So that's how a battery would work, and how these electrodes work is a similar fashion. First, we'll look at the ion selective electrodes. These consist of membrane selectivity permeable to a single ionic species. The membrane potentials are caused by the permeability of certain types of membranes to selected anions or cations. Ion selective membrane is the heart of an ISE as it controls the selectivity of the electrode. We usually have membranes that are made out of a polymer or glass, and the tests that are done with this type of testing are things like pH and electrolytes such as potassium, sodium, chloride, calcium, lithium, magnesium, and CO2. Here's some pictures of what some of these electrodes look like in the chemistry analyzer. The first one we'll look at is a pH electrode, which is a type of electrochemistry. This is considered an ion selective electrode, and it consists of a silver wire coated with silver chloride immersed in a solution of hydrochloric acid and placed into a tube containing a glass membrane tip. The membrane is only sensitive to hydrogen ions, and we have a picture of this on the right-hand side. Here's our silver chloride probe and the hydrogen ions in the solution. When the pH electrode is placed into the test solution, movement of hydrogen ions near the tip of the electrode produces a potential difference between the internal solution and the test solution. It's measured as pH and read by a voltmeter. So you need to be familiar with the silver chloride being part of the pH electrode and the fact that it is an electrochemistry type of analytic technique. The next thing we'll look at here is the Coulter principle. It relies on conductivity of blood cells being lower than that of the salt solution used. The cell suspension is forced to flow through a tiny orifice in which two electrodes are on both sides with a constant current. Each time a cell passes through the orifice, as you can see in the diagram below, resistance causes a spike in the electrical potential difference between those two electrodes. Those pulses are counted, and the amount of pulses refer to the amount of cells. So this is a much faster way to be able to count blood cells than doing it one by hand. Electrophoresis is the next technique that is used in the clinical chemistry department. This is the migration of charged solutes in an electrical field. Solutes take on an electrical charge by becoming ionized and moving towards either the cathode or the anode, depending on the type of charge the solute carries. I have a depiction on the right-hand side where the sample is added to the different wells. Now, this is made out of a auger, which is kind of like a, I'm going to call it like a Jell-O jiggler, if you guys have eaten those before. And you add the sample to that. Now, that gel, depending on its density, will have these proteins travel towards the anode if they are negatively charged, which in most cases we do make them negatively charged if it's a protein. So the samples are added to the wells, and as you can see by step 4, we've got 3 different samples in here. Now, the sample is going to travel, depending on the charge of the molecules, the proteins will travel from the cathode towards the anode. And they will separate, the different proteins will separate out. Okay, so by the time it's done, we'll have all these different separations on here. We can then go through and stain this and look at it to see exactly which ones are present. The rate of migration in electrophoresis is dependent on a few things. The net electrical charge of the molecule, usually at a pH of 8.4, proteins are negative and travel from the cathode to the anode. The size and shape of the molecule. Some proteins are really big and they can only travel so far. Some are really small and travel really fast. The electrical field strength is important. If you have too much electricity, it's going to run super fast. If you don't, it's going to go really slow. You have to look at the properties of the supporting medium. Sometimes it's too thick, sometimes it's too thin, so you want to make sure it's just right. And the temperature. You don't want to be too hot or too cold. The electrophoretic mobility is directly proportional to the net charge and inversely proportional to size and viscosity of the medium. Here are some of those support mediums, like I talked about, the like Jell-O jiggler type of consistency. This is what gives it that consistency. Either cellulose acetate, or more commonly used, agarose, which is what we'll use in our laboratory. It's used in the separation of serum, urine, spinal fluid proteins, hemoglobin variants, isoenzymes, lipoproteins. The pore size is large enough for all proteins to pass through, but separation is based on the charge to mass ratio of the protein. Another one is polyacrylamide. This is where the proteins are separated on the basis of both charge to mass ratio and size. It separates proteins into 20 or more fractions instead of the usual 5. This is widely used to study individual proteins. The general procedure is we run it through an electrical current to separate it. We then have to put it on a densitometer in some cases to stain the protein on the gel so we can actually see it. Then we put it under a detector to read the density of those colors to see exactly how much is there, and that'll give us a quantification. The next analytic technique is osmometry. Osmolarity is very important in the body, and when things flow through like cell membranes, it's very important to keep the balance of equilibrium between the inside of a cell and the outside of a cell so that things don't swell or shrink. In order to do that, we make sure the osmolality within the human body is normal. We do this and test for it using osmometry. It's used to test the concentration of solute particles in a solution. If you have too many solute particles in the external cellular environment in the body, it can throw off the osmolarity between the inside and the outside of the cell, causing the cell to shrink or swell. So what we do is we measure it indirectly by measuring one of the colligative properties. In most cases, I've done a freezing point osmometry, but there's also boiling point and vapor pressure available. And these change proportionally with osmotic pressure. If we have a high osmolality in our sample, it could mean that they've had ethylene glycol poisoning or ethanol poisoning. Here's what it might look like. There's a stirring wire. Put the sample in, there's a stirring wire, and they freeze it. And the longer it takes to thaw, the more or the less solute particles there are. So I guess it uses a technique where they freeze it and see how long it takes to thaw. Chromatography is our next analytic technique. This is a physical process where the solutes of a sample are separated as a result of their differential physical interactions between individual compounds in the stationary phase. The basic components are the mobile phase, which carry the sample through a bed, layer, or column containing the stationary phase. The mobile phase can be gas or liquid, and the stationary can be solid or liquid. I'm going to show you some pictures in a minute. There's a column that holds a stationary phase, and we end up with separated components. There are some different separation mechanisms. Chromatographic separations are classified by the chemical or physical mechanism used to separate the solutes. For example, we can use ion exchange, partition, adsorption, size exclusion, and affinity mechanisms. Clinical use is primarily of ion exchange and partition. So here's a picture of something similar to what you'll be performing. This is thin layer chromatography. This is where a thin layer of sorbent is coated on a plate. Think of it as a piece of paper towel. Okay, if you took a piece of paper towel and you had a wet bucket and you put it in there, you'd notice the water start to wick up the paper towel as you hold on to it. Similar scenario. A sample is placed at a spot near the edge of the plate. So here's all our samples. I'm going to put them on the bottom, okay? Now what's going to happen when you put this plate inside the solvent, there'll be a little bit of solvent here down in the bottom. All of the solvent is going to start to travel up and up and up and up. As it does that, it's going to carry your unknown sample a certain distance. There's a mobile phase, which is the solvent in the bottom, and it needs to be kept in a closed container, otherwise it'll just evaporate. And one edge of the plate is placed in the solvent, and it'll migrate up the thin layer, dissolving and carrying sample molecules up. They will only go so far depending on the interaction of the solvent. So they will stop at a certain point, and we will take a measurement to determine what type of sample that is. We get a little fancier here with high performance liquid chromatography. Liquid chromatography that uses pressure for fast separations, controlled temperature, and inline detectors. So you can see there's a series of columns that it goes through to separate them. Gas chromatography uses separate mixtures of compounds that are volatile or can be made volatile. It can be gas solid or gas liquid. And gas liquid chromatography is commonly used in the clinical labs. But here there's a cylinder of mobile gas, and it will separate it out, and it'll be detected on the end as to determine what is there. A lot of times gas chromatography is connected with mass spectrometry. It's a qualitative and quantitative technique used to measure a wide range of analytes, commonly coupled again with the gas or liquid chromatography as the detector piece. It ionizes a target molecule and then separates and measures the mass of it to try and determine exactly what element it is. Here's an example of what a readout might look like as it comes out of the mass spectrometer. So, and gas chromatographer. Well, they'll see a peak for each thing that would be present. So over time, the things that come out fastest are probably going to be the most volatile, and things that come out the slowest are less volatile. And that concludes our section on analytic techniques.